let's try to understand what is a linked list. So, a linked list, how would we define it? A linked list is a linear or at times circular homogeneous, I'll explain each term one by one, homogeneous data structure used to store elements in non-contiguous memory locations. Okay, so there are a number of terms I've used here. The first one is, it is a linear or circular list. Now, why do I use this word linear? The reason for me using the word linear is, we can have linked lists of two types. We can have linked lists of two types. Our linked list can be a linear linked list. That means arranged in a row, which has a definite starting point and a definite ending point. And we could also have circular linked list, which will simply wrap around. Okay, so that's why I've used these two terms. So we can have linear linked lists as well as circular linked lists. We'll look at them one by one. And it is also homogeneous data structure. Okay, it is a homogeneous data structure. Now, why do I say it is a homogeneous data structure is, generally you would use linked lists to store elements of the same type. We would have linked list of integers, or linked list of characters, or linked list of strings. That is why we are calling it a homogeneous data structure. And it is used to store elements in non-contiguous memory locations. Non-contiguous memory locations. What happens is, now in order to understand non-contiguous memory locations, it's better to have a brief knowledge, or it's better to briefly go over what is contiguous memory allocation. Now, there is a popular data structure by the name of array. Now, what does an array do? An array stores elements in contiguous memory locations. It stores elements in contiguous memory locations. That means if this array is a character array storing character constants in each cell, let's say this is my character array by the name of CH, then if the first cell in this array has an address of 1000, then the next cell will have an address of 1001, then one next to it will have an address of 1002, and the last one will have an address of 1003. The rule for contiguous memory allocation is, if you know the starting address, you can find the address of any element next to it just by running over, or just by going over the size of the element stored in the array. That means we know that characters generally take up 1 byte. So if I know the starting address, then I can move over to each element by adding 1 byte to it. That means I'm starting at G. I know its base address, or I know the starting address, which is 1000. Now if I add 1 to it, I'll get 1001, which is the address of my next character constant in the array. Then again, if I add another 1 to it, I'll get 1002, which is the address of the next character constant, and so on. So this is what I mean by contiguous memory allocation. Memory slots are given to the elements consecutively. Now, what about non-contiguous memory locations or non-contiguous memory allocation? In non-contiguous memory allocation, what happens is there is no provision or there is no need to store elements in consecutive memory locations. We can have elements located at different places in memory connected to each other by means of links. So that is what we mean by non-contiguous memory locations. And a linked list is a classical example of a data structure which stores data using non-contiguous memory allocation. So let's just take up an example. Let's say I have a single linked list of integers. Now, this single linked list of integers will have two parts to it. Each integer will have two parts to it, right? See, the first part is called the data part, and the next part is called the address part. Now what happens is this address part will store the address of the next node in the list. So let's say this is my node. What is a node? A node is simply a block of memory. This block of memory is obtained from the primary memory, or it is requested. We generally send out a request to the operating system, and if enough memory is available in the memory bank, the operating system grants our request and we are given a chunk of memory. Now, for linked lists, what happens is these chunks of memory or these blocks of memory need not be contiguous, need not be present one after the other. They can be present throughout the memory map, not necessarily in increasing order or decreasing order. So let's say the first node that we have here, let's say it has an address of 2000. Okay. Now, let's say the second node has an address of 2050. The third node has an address of 4000. And the fourth node has an address of 6000. So what will happen is, in this address part, sometimes also called the link part, we will have the address of the next node. So which is the next node in the list? This one. So this address part will contain the address of the next node in the list. What is the address of the next node in the list? 2050. So this will contain 2050. And as a result, it will be pointing to the next node. Okay. Similarly, this node will contain the address of the next node in the list. The address of the next node in the list is 4000. So this will contain 4000, and as a result will be pointing to the next node. This pointing is a logical representation. You don't have a memory hierarchy, or you don't have a particular memory module with arrows pointing between consecutive cells. These arrow representations are merely for our convenience so that we can visualize a linked list as a chain of elements, nothing more. These arrows do not exist in the physical memory, mind you. And this one will contain 6000, right? As a result, we'll be pointing to the next node. And remember, the last node of a linked list contains null. And generally, we show null by grounding it. Okay, this is how we show a null. This is my null. The last node of the linked list will always contain null. And also, the first node of the list will be pointed to by a special pointer called the head pointer, which will contain the starting address. So the starting address of my list is 2000 because this is the starting node and it has a starting address of 2000. So head will contain 2000, and as a result, head will be pointing to this node, right? And what about the data part? The data part can have any valid integer value because we are considering a linked list of integers. So I'll have in my data part integer values. So let's say 3, -1, 7, and 99. So this is what you call a single linked list. A single linked list. Right? We'll go over each of the linked lists in detail, but this is just an introductory video just to make you understand how linked lists are organized in memory. And one more thing, why am I calling it a single linked list? It's called a single linked list because from every node you have one pointer. See, this node made up of the data part and the address part has one pointer going out from it. This node again has one pointer, this one has one pointer, and so on. Had every node taken out or brought out 2 pointers from it, then we would call such a linked list a double linked list. We'll look up double linked list in detail in the later videos. For now, try to understand what a single linked list is and why is it called so. Since every node has only one pointer coming out from it, that means it has only one address part. Every node has only one address part, as you can see, one address part, one address part, one address part, one address part. Had you have 2 address parts for every node, then such a linked list would have been called a double linked list. Okay. And remember, the primary constituent or the primary component making up or responsible for building our linked list is called a node. The primary component is the node. Using multiple nodes, we build our linked lists, and a node will have 2 parts to it. It will have a data part. This is a very elementary node. I'll just discuss about it in details. Let me just complete this. I have a data part and I have an address part. This is how a basic node looks like. Now it doesn't mean that there'll be only one data part all the time. There'll be only one address part all the time. But this is the general convention. We can have multiple data parts to a linked list. We can have multiple address parts, just like I told you a while back that we can have a double linked list where each node will have 2 address parts. So like this, we can extend the functionality of linked lists as our need arises or as our applications demand. But just to keep things simple, for an introductory start on linked lists, it is better to consider the node in this fashion, which has one data part and one address part. So I hope this video proves to be helpful. Thank you.